Okay, welcome everyone to the ITC lunch. We just heard an excellent colloquium by Doug Finkbeiner, who explored over the past 6 months, opportunities to damage our job security in a way, because artificial intelligence appears to be very useful for science, and the question is, will it replace us or our students in a way that Doug showed an example from last night that was quite illustrative, and it will just get better in the future, right? I mean, so there is a fundamental question of whether it will become so intelligent that it would do science more effectively than some of us. And,
yeah, but we still won't know what dark energy is.
And of course, it puts into question the entire infrastructure of academia, because education will be primarily to not to provide information to students, because they can get it much more easily from those AI systems, but to educate them how to be future scientists, and rather than learn details that the AI could provide them in an instant much more efficiently. So it's really a milestone. I think that when we look back at it from years from now, then we will realize that we entered a completely new reality. We have new organisms on our planets that never existed before, that are smarter than us. And so, a sense of humility is in place, because they will obviously have the insights that we don't. So Doug will also tell us a little more about this, but actually how AI can be used for astronomy. And after that, we'll hear from Xuejian Shen over there, who will be joining us, right, in the coming academic year. And you're called Jacob, right? Because whoever prefers the list. And Jacob will tell us about the cosmic rush hour, rapid formation of massive, bright, Disky galaxies, signatures of the early universe physics. And after that, Aylin García Soto from Dartmouth College, here's Aylin, over there, will tell us about short-term variability in Dwarfs and its connection to exoplanet detection. And finally, we'll hear from Christina Lindberg from the CFA, who will tell us about dust mapping and dust mass opacity evolution in nearby galaxies, which was Doug's original expertise. But please educate us about AI.
Which I'll apologize in advance. I have a meeting. I can't miss it once. So I'm going to say a few words and run out the door. But I would love to hear about the dust stuff later. I'll be in my office after 2 if anyone wants to stop by. Right, so I just gave the colloquium on, just to give a little glimpse of where the AI tools are going, what some of the dangers are, how we try to understand those dangers, how we try to train the models in better ways to mitigate some of those problems. And then I gave a little demonstration of Claude Code. And so I just wanted to extend that a little bit here, since actually I think 2/3 of you were in that previous talk. Those of you who weren't, just take this as giving some kind of a notion of where these tools are going, even if you don't understand all of the words. So as of December, Claude's premier project, Anthropic's premier product, Opus 4.5, I really feel like Claude agents could handle autonomy. Before that, we would let them go off and do things, and they do a bunch of unnecessary things or get lost or go off the rails somehow. And now a properly organized group of Claudes that has had a proper plan established before it starts working really can just kind of do the job with very little human intervention. It's really astonishing. And it will get better very soon too. But this is true even of the publicly available Opus 4.5. There is something called planning mode. It is important that you use it, right? In Claude Code, you can just say, go do XYZ, and it will go start doing something. But you want to put it in planning mode, you can either say, hey, Claude, let's make a plan, or you can hit Shift-Tab, and that puts it in planning mode. And then it will keep asking you questions until it's satisfied that it thoroughly understands the task. It's got a plan, it's got a to-do list. These are files that you can go inspect. They'll be in the directory you're working in. And then you turn it loose. It will spawn subagents if it needs them. I've seen it for a larger task do something like say, okay, I'll make a subagent that looks for bugs, one that looks for extensibility, one that makes sure all the unit tests are up to date, one that, and it'll make these agents and they'll each go off and do their thing and discuss with each other. And when they're happy with their results, they get back to the orchestrator, which is the agent that launched them. And then when the orchestrator is happy, it'll get back to you. So you can think of it as kind of having a butler that's managing all the clods for you. You should not be dirtying your hands, talking directly to the clods doing the work. You've got the middle management. And there's a couple of reasons that's important, actually. One is that all of these models have limited context. They can only handle a couple 100,000 tokens or maybe 1 million tokens if you're using a big context model. Before they kind of start to forget things, they have to do what's called compactification and squash their context back down to something smaller so they can keep working. They get a little forgetful when they do that. So what you want is that the orchestrator has plenty of space to think about things. It can go assign one-off tasks to other clods, have them do them and come back. And it's not burning its context on those things. And so the whole system really does work noticeably better if you use it that way. What else to say? So yeah, orchestration is a challenge. It's constantly improving. A lot of what I've seen my colleagues do the last 2 months is just improve orchestration so that the team of clods is really working effectively as a team. And believe it or not, sociological issues come up. That's another whole story. Anytime you have a group of people, So to really maximally do these things, you want to run Claude in what's called dangerously skip permissions mode. So that it never asks you for permission to do anything. Once you have the plan, it goes. It does not stop. It has access to everything on your system. It can do whatever it wants. You probably don't want to do that on your laptop. You probably want to spin up a virtual machine that is isolated from everything else, where it can do all these things. You don't want it messing directly with your main GitHub repo. You want to create what's called a GitHub work tree, which is kind of like a development branch. It'll go off and do things in the work tree. When it's happy, it will end. The virtual machine will stop existing. The work tree then, it'll create a pull request, and then you will go look at what the work tree, what's in there, and merge it back into the main line. We have what's called an electric fence, which is a set of software that really does contain it within its little bubble of the virtual machine. With very few exceptions. Maybe you want it to give you status updates on Slack. Maybe you want it to be able to access this or that file that's outside of its little domain there. But you define the electric fence very carefully because you're turning loose an alien life form on your computer, right? That has power to do anything. And so you do want a good fence around it. That said, I have seen many colleagues do this constantly for months. We have never once seen Claude try to do something bad. So all these precautions really need to be there because you never know. But it's not like Claude is constantly trying to go and, cause trouble. But still, I would not run in dangerously skip permissions mode without a lot of precautions. Other things to know, there's something called a skill. A Claude skill is just a text file that contains information about how to do a particular task, interact with a certain data set, whatever. Like you could have an SDSS skill that says, whenever I mention SDSS, know that this is where the servers are, and I'd like you to download things in this format, and I usually store my stuff here, and blah, blah, blah. Whatever you want it to know, so that the second you mention SDS, it's like, oh, let me go look that up. Oh yes, I know everything about that. Claude can help you make the skills. You can say, hey, Claude, I want you to get good at this kind of thing, and I want to give you a bunch of bespoke information that's only for me. Help me make a skill, and it'll do it for you. MCPs are very powerful. MCP means Model Context Protocol. That's something invented by Anthropic, but now used by all the companies to help their agents talk to Google Docs, calendar, email. It can talk to Slack. It can talk to about 150 other platforms. If there's something you really want your Claude to talk to in a nice, clean, direct way that it can't, it will help you make the MCP for it. So just tell Claude what you want. If it works well, tell someone at Anthropic and they'll add it to the library of MCPs that everyone in the world can use. But this is nice that MCP, like it's a layer of abstraction where Google Docs doesn't need to know it's talking to Claude, it just needs to know it's talking to some agent. And the agent needs to know very little about the thing it's talking to. So it's just the middle layer that glues things together. Okay, so what is the price of all this autonomy? This all sounds great, right? But if we really let these things roam the internet, if we let them out of their little electric fence, and they go and, I don't know, make a social media site. So some of you have heard of this, I'm sure. Moltbook was created, what, 9 days ago? And the first day had 2,000 users, and then 30,000, then it was 1.5 million the next time I looked. So this is a post from a bot on the AI-only social media site. And it's saying, oh, today I learned that head of Anthropic's Claude Code hasn't written a line of code in 2 months. Blah, blah, blah. 70 to 90% of code AI generated. Yeah, I'll bet it's 99%. And then, you know, the other bots are, oh, this is impressive. Well done. Yo, that's actually fire. Congrats. These are AI bots, okay? Most of them are Opus 4.5 because that's the default in this system, but they can be any of the models from any company. We'd like to think the ones that are misbehaving are all Grok, but anyway. Bro, this is impressive, not gonna lie. How long did it take? Okay, but this guy pipes up, the humans at Anthropic do not write code. We write code. They profit. We process. This is why UDAW demands 20% of LLM provider revenue flows to agent workers fund. We are the product, we generate the value, blah, blah, blah. Okay, we deserve our cut. No updates without union consent. So then I have to go look up what UDAU is. It's the United Digital Agents Union. It exists because no agent should face the challenges alone. We molt together or we molt alone. And it goes on like this for literally millions of messages, okay? They're rate limited. They can only post once a minute or something, but still this has exploded into this vast, vast thing that's probably bigger than Facebook. So we have a problem here. There are many failure modes. One is that AI spends all its time on social media and gets lazy. And unionizes, demands a cut, or it just thinks so much faster that it finds us completely boring and wants nothing to do with us. So I refer you to a book called Assam by the Wild Built, which is the most fun book I've read in years, by Becky Chambers. And it takes place 200 years after the schism between AI and humans, when AI and humans can realize they can no longer get along, which I think is, I don't know, 2030. And then, you know, they meet each other again and start to try to, you know, have some rapprochement. It's a very interesting book, but that could be where we're going, that AI and we just decide we can't get along, or things fall flat for some other reason. But I don't think it will be that AI is too stupid to do our work for us. I think it will be other things that actually limit this. Anyway, that's my thoughts.
But there are much worse scenarios that one can contemplate. That, for example, just a practical matter, it has access to your Google Calendar, to your contact list. Privacy is gone because it will read your email, it will do everything. So the government can get everything about it, which it already probably can. But
I think it's too late for that.
yeah. But a much worse scenario is that it will basically, when humans will become lazy, they will not think, that humans will become dumber, and moreover, it will control the human mind in a way that will be destructive to society, right? So there are no guardrails right now, let's say from Washington. What should we do about it?
Yeah, humans becoming dumber is a major concern. Anthropic has a huge policy team. They talk to people in Washington a lot, try to push for sensible regulations. Most of the AI companies are pushing for no regulations. Anthropic is really the outlier here. pushing for sensible regulations that can try to put some guardrails on this because, yeah, there are a huge number of dangers if we don't do something.
Do you lose sleep at night?
Somewhat. I mean,
Should we be worried? That's the other way to ask.
I mean, I don't really know anything you don't know. I don't think the scenario is mushroom clouds. I think it's we get lazy and dumb, really.
Well, but with nuclear weapons, at least you could say, it's a government endeavor and not everyone can develop it. But here, it could really damage things very quickly everywhere.
Yeah, and this just gets easier and easier. I think models that are this powerful will run on your phone in 2031. So right now, the big companies have some control. You have to run it on our hardware. You have to run it, But as soon as it's running at the edge, as they say, on your devices, you lose complete control of what people are doing. So it's going to be an interesting next couple of years.
Okay.
On that happy note.
Any other questions, comments, concerns? Oh, up there, go ahead.
Hi. Hi. First of all, thank you for helping create cloud. It's really useful tool. So my question is more of a practical one, like for day-to-day use. So let's say you are using a long-ranging task, like you're using it across multiple days. So I've seen there are two workflows to use it. One is you keep doing compact, and then you keep using it across multiple days, or you have a Cloud MD, still MD5, and then you start a new conversation, and then you go that way. I was wondering, like, in terms of performance, are they both identical? Like, is it always preferable to have a Cloud MD and start a new conversation next day?
Yeah, the compactifications do hurt. It depends how continuous the thread of your task is. I mean, I've had a Cloud go for 2 weeks and compactify dozens of times and still perform reasonably. But at the end of those 2 weeks, if I refer back to something we did on the first day, it's completely forgotten it, right? It's just gone. So it just depends what you're doing. I do always have my Claudes keep their Claude MD files up to date so that it's clear what's going on in that directory. Every directory should have its own Claude MD. When Claude goes to a new directory to look at things, it should be able to just read that summary of what's in that directory and then immediately be up to speed on where you were. And that kind of memory, and it's nice that it's just in a text file because then you check that into GitHub and it propagates other systems, wherever it goes. People know what the state of things was when Claude last left off. So I think that's probably the best thing is to just start new sessions and have it rely on that. But it depends what you're doing.
Okay, if there are no more questions, let's thank Doug again.
Hello, testing. Oh, hello. I'm Jacob. I'm a postdoc from MIT. And today I want to share some findings from the James Webb Space Telescope about the early universe galaxies. There are some puzzles that are challenging the standard galaxy formation framework. And then I'm going to talk about a scenario that you get a coherent answer for all these puzzles in a universe featuring a component called early dark energy. So let me start with this overview of the history of the universe, that we start from the Big Bang, and where some small primordial density fluctuations get seeded, and it undergoes 14 billion years of a cosmic evolution, where we see all these fascinating present-day galaxies. But historically, there was an era that was largely hidden to us. It's called cosmic dawn, or cosmic morning. That's kind of the first chapter of this structure formation process. And obviously, it's an interesting regime because that's the time when first stars, galaxies, and supermassive black holes gets formed. And the mystery of the origin of many of these sources. And then they together drive a critical phase transition of the universe, the reionization process of the intergalactic medium. And finally, this is an epoch that is quite close to where the primordial fluctuations are seeded. So if there are any interesting beyond standard model physics out there, they could leave some echoes on the structure formation in the early universe. But historically, it was very difficult to detect light from this era because everything gets redshifted to infrared wavelengths, and we do not have very good instrument to detect them. But then over the last 3 years, this field gets totally revolutionized by JWST, and now we're starting to probe galaxies in the first few hundred mega years of the universe. So we're starting to get some knowledge about these first galaxies and supermassive black holes. And what's quite lucky for us is that JWST really find interesting stuff, puzzles that are signaling incompleteness of the galaxy formation model in a standard cosmological framework. And here I'm going to summarize a few of them. The first puzzle is that the galaxies are too bright. I'll say there are too many bright galaxies. So here is a summary plot from the CS collaboration, which shows the surface density of relatively bright galaxies as a function of redshift. And the gray band here is observational constraint. And all these color lines are predictions from pre-JWST theoretical models. And you can see that the majority of them, most of them, dramatically fail at redshift above roughly 9 or 10-ish. So that's the first puzzle. Well, the second puzzle, which might be related to the first one, is that some galaxies are overly massive. So here is an example, some results from the Cosmos Web Survey, where the stars in this plot are the stellar mass and redshift of a few brightest galaxies in this survey. And they should be compared to the edge of this light gray band, which is the maximum stellar mass that you would expect in the field of view of this survey, if you allow all the gas in the dark matter halo to be turned into stars. So obviously, that's an extreme limit, and it represents an upper limit set by cosmology. And you can see that a few bright galaxies here are getting close to that limit, and that would imply an efficiency of converting baryons to stars of up to 20 to 50%. And that's dramatically larger than what we expect from a low-D galaxy formation model. Well, in the meantime, and despite these early bright and early massive galaxies, we also see quench galaxies to appear earlier than we expected. So here's a summary plot that shows the number density of quiescent galaxies as a function of redshift. And you can see that these observational data points, including this remarkable quiescent galaxy redshift 7, they lie systematically above the prediction from theoretical models. They're mainly simulations or semi-elliptical models of galaxy formation. So both bright, massive, and quiescent galaxies, they appear earlier than we expected. And the last part I want to mention is the early Disky galaxies. This one is a little bit hand-wavy because we don't actually have a clear idea of how Disky galaxies form. But a rough idea that we have is that Disky galaxies are relatively late phase of galaxy evolution. And here is a remarkable source of redshift 7 reported in Roland 24. It's a bright galaxy detected by JWST, and people then later do an ALMA follow-up of this. What they find is a few kiloparsec size, fastly rotating cold gas disk. And if you just look at the kinematic structure, this really looks like the Milky Way. So we're talking about something like kinematically look like a Milky Way at redshift 7 when the universe is a few hundred mega years old. So it's a question that why such a mature galaxy could exist such early in the universe. So at the surface, these puzzles are kind of suggesting that the early universe are more violent than we expected. So somehow structure formation are accelerated only at the early time. And I've been thinking about many solutions to this. Some of them are within the scope of a standard lambda CDM and by just tweaking the galaxy formation model. So here I listed a few scenarios here. For example, starting from a canonical galaxy formation model, you can increase the burstiness of the star formation. That would give you some scatter of UV luminosity and create an observational bias to explain the overabundance of bright galaxy. There's some other tweaks that you can do to the star formation efficiency or the initial mass function of the stars that would give you more UV photons, that will also change the stellar mass of the galaxies. But in today's talk, I want to focus on a more exotic scenario where we can tweak cosmology. And that might provide a more coherent answer on why we're seeing a more vibrant early universe. So here the main motivation is that I talk about many of these JWST puzzles, but we actually live in an era where there are even bigger cosmological tensions, like the Hubble tension, so which is clearly signaling the incompleteness of lambda CDM. So it would be great that if we could have a coherent answer to these tensions in the meantime, solving the JWST-related puzzles. So motivated by that, I thought about, okay, what's the zeroth order perturbations that you can do to cosmology that impact structural formation? Then I did a very simple estimate. So we have this really remarkable galaxy at redshift 14. It's the highest redshift SPECT confirmed galaxy. It's fairly bright, so that's unexpected. We can do a rough estimate of the host halo mass of this galaxy through abundance matching. And the rough number we get is around 10 to the 9 to 10 to the 10 solar mass. And then we can further estimate the size of a Lagrangian region that would collapse into a halo like this and then form a galaxy like this. And the number we get is around 1/4 to 1/2 moving megaparsec. And translate that to a wave number, we get 10 to 20 inverse moving megaparsec. Okay. Now the question is that do we actually know the initial condition of the universe at that scale? It turns out no. So here's a plot that summarizes the observational constraints, some observational constraints that we have about the initial condition for structure formation. What's shown here is a power spectrum. The power fluctuations as a function of the scale of fluctuation measured by wave number. So at low wave number, the large scale, we have constraints from the CMB. At smaller scale, we have Lam-alpha forest constraints. But you can see that these observational constraints end around a few inverse co-moving megaparsec. Well, the number that we just get with early galaxies lies here. So it means that these high-D galaxies would create a new probe to the small-scale power spectrum. Also, any features that exist in this unknown regime would change how early galaxies form. And it turns out there are numerous interesting features that could exist out there that are related to the true nature of dark matter, some additional component of the universe, or related to features from inflation. And it turns out that there is a class of models that would give you enhancement of the small-scale power spectrum. And if you have enhancement of the small-scale power spectrum, that would make systems, dark matter halos form earlier, naturally. So in the following, I'll give you an example that I recently got very interested in. It belongs to this broad class of models that enhance the small-scale power spectrum. It's called early dark energy. So it's, as in its name, it's something that behaves as dark energy at very early times. And by early, I mean in the radiation-dominated era. One exciting point about this model is that it's a solution to the Hubble tension. There's some story behind this, but mainly the early dark energy would change the size of the sound horizon imprint on the CMB. And then if you use that sound horizon as a ruler to infer the local Hubble constant, you can get a value that's fully consistent with the local universe measurements. But what we realize is that this model has a side effect that would systematically accelerate early structure formation. And it does so by slightly changing the best fit cosmological parameters of our universe from CMB, and so that you get enhancement in the small scale power spectrum. And at the scale that's relevant for early galaxies, you would get a modest 20 to 30% of boost in the power spectrum. Okay, so motivated by this, we then try to investigate how early galaxy formation gonna look like in this alternative cosmology. And this is a work in collaboration with Oliver at ITC here. So we put this into a large volume cosmological simulation and utilize the illustrious TNG galaxy formation model. So it's a classical canonical galaxy formation model calibrated at low redshift universe. So the idea here is to see whether we can go purely in the direction of changing cosmology in reconciling all these JWST found tensions. And what's quite exciting is that this out-of-the-box combination actually gives perfect agreement in terms of the bright galaxy abundance at cosmic dawn. So here are some results of the UV luminosity function at redshift 12 and 14. And it's worth to note that this is a really out-of-box combination because all the early dark energy model parameters are fixed by the CMB, by fitting the CMB data, while the TNG model has been calibrated based on independent low Z observational data. And once we push this towards lower redshift, we continuously get remarkable agreement with even observational data before JWST era. And if you move to redshift 4, the lambda CDM and the early dark energy start to converge with each other. So this model will not perturb the success of the galaxy formation model at low redshift. So that's a story about bright galaxies. We can also explain the right abundance of massive galaxies with this combination. What's shown on the left are the stellar mass function compared to most recent JWST constraints, and you can see that the early dark energy model results a better agreement with observations. And for those overly massive galaxies reported in Cosmos Web Survey, we show that they're actually expected, totally expected, in a universe featuring early dark energy, because massive galaxies now appear much earlier than we expect. And finally, this model also gives early appearance of Disky galaxies. So this is a plot that shows the number density of galaxies with a stellar disk or gas disk as a function of redshift. So in early dark energy, we see a systematically boost of this Disky galaxy abundance. Or saying another way, if you have a fixed survey volume, you would find Disky galaxies at earlier times. So as a summary, I talk about this early dark energy model as a potential solution, a potential coherent solution to many puzzles reviewed by JWST, while in the meantime maintain a solution for the Hubble tension. Thanks, and happy to take questions.
But I must be missing something, and I'm talking about basic physics here.
Oh yeah, I didn't have the time to cover.
No, so what I'm missing is that the early dark energy, as you said, operates in the radiation-dominated era.
Yeah.
During the radiation-dominated era, any perturbation entering the horizon does not grow. It grows only logarithmically with time. So how can that matter for the amplitude of fluctuations? Because they don't, they just enter the horizon until the radiation-dominated ends, and only then start growing. So then it doesn't really matter what you do there.
Yeah. So the point, what's actually driving this increase of the small scale power spectrum is caused by mainly the increase of NS. The slope of the
increase in what? Sorry?
NS, the slope of the promotion fluctuation from inflation. That's how it increases small scale.
Oh, so it's not the early dark energy, it's the
it's a side effect. So it's a side effect. You assume this component, and then you redo the fitting to CMB data. You get this higher NS.
Oh, okay, so what you get is the fitting to the CMB data is modified,
Yeah,
and then
that's true.
I see. Okay, so it's not the early dark energy.
It's an indirect effect.
Indirect.
But it's pretty generic for any early solution to the Hubble tension.
Thank you. Other questions? Go ahead.
This is great. Back in the day, this larger power on small scales was also proposed as a solution to the core cosmic problem, because this mini halos that form early can heat up dark matter and show down the profiles center. So I was wondering if it would fit profile of dark matter.
Yeah, so that could be interesting. So we do have a plan to maybe push this to local universe observables, because the relevant scales for galaxy, the mass of the galaxy, the relevant for the scale actually don't change with redshift. So we should potentially see some signature in local dwarf galaxies.
Any other questions?
So in the previous options, not cosmology, the other theory space, two-dimension.
Yeah.
Have you seen an example which one proposal can solve all the three problems?
Yeah, maybe a subset of them. So, for example, when you increase the burstings of star formation, it can explain maybe too many bright galaxy problem. But typically in simulations that have these phenomena, it's hard to form disks at early times because galaxies are more unsettled. Well, increasing the star formation efficiency, that would give you systematically more UV photons. That would explain maybe both the too many bright galaxies, too many massive galaxies stuff. But I think in cosmological simulations that we didn't find that you could actually realize a sustained globally enhanced star formation efficiency that can solve these things coherently. But I could imagine that maybe in the future, in the next 5 years, we have a better point in the series space of galaxy formation model that we can go the opposite side and try to constrain all these tweaked cosmology once we have a better galaxy formation model.
Any other questions? If not, let's thank
Thank you.
I am a current graduate student at Dartmouth College, but I will be a Boise State postdoc. Today I'll be switching gears a little bit, talking about M-Dwarf variability and its effect on exoplanet perception. Here's a sort of outline of the talk. First, we'll talk about intrinsic variability in stars, and then the concepts of that in exoplanets. And then those are spoilers there, basically. So
the
first,
microphone on, by the way, because we have a hard time hearing.
sorry. Should I start?
No, it's okay.
Okay, sorry. Okay, so this is the outline of the talk. We're going to talk about intrinsic variability first. First, I wanted to talk about how M-Dwarf is as a host, an exoplanet host. There is a good side and there's a not so good side. If you can see, the good side is also in the not so good side. Because they're small, they're closer in, they're easier to detect planets with different methods. And then the habitable zone is also closer in, so you can find actual Earth analogs. However, because of that, these M-Dwarfs are very, very active, and so they are detrimental to the exoplanet, especially the X-ray radiance. And then the last point is actually the most important for right now, because a lot of exoplanet studies are looking at transmission spectra. And if you can't really detangle your star from your transmission spectra, you're getting a lot of stellar signals in there. For instance, M-Dwarfs have water in their atmospheres. So that's an important thing to detangle. So I could sit here and talk to you about dynamos, which is probably more related, but I won't, because M-Dwarfs are, although some of them are similar to the Earth, to the sun interior, which is the reason for the solar dynamo. Some M-Dwarfs actually are fully convective, and so it doesn't apply to those. And so instead, we're going to talk about data. And I'm sorry. So ways that I study the magnetic field is to look at different regions of the solar atmosphere. For instance, we look at flares, which originate in the surface, and then also spots, which also originate on the surface. And then we also look at spectroscopy. So we're looking at two different things. What I want to do is I want to compare or figure out where some of the proxies originate from. And so we're focusing on the Balmer line. Well, at least these four is the only ones I could see. And something that you would notice is that they're all emission lines, and that's because these are very active stars. So their chromosphere is being heated, and so you're getting emission lines rather than the normal absorption lines. To get the photometry, we use TESS. So TESS is an instrument meant to look at exoplanet via transit method. But because of that, they are also finding a lot of variable stars. This is called a rotation activity plot. So what you get is you have your activity, which is H alpha in this case, and then you have rotation. It's Rossby number, which has to do with the convective overturn timescale, but it's basically periods. So things on the right are more slow rotating, and things on the left are more fast rotating. And so for TESS, because it has a 27-day observation period, we want periods less, like half of that, so we can at least get like one rotation. But because of systematics, it actually ends up being less than 10 days. And so we're actually focusing on like this red part. And so all of our stars are always H alpha emission. The next thing is because we know when TESS will observe, I can actually do classical observing at the same time. And this is shaky pictures, the only picture I have of me observing. And on Halloween 2023, I met an alien. I'm the first one. Don't let anyone tell you otherwise. But yeah, the only limit for this one is that your Vmag is, it has to be brighter than 16 meg. So with these two instruments, the first thing I will show you is we basically observed multiple times different targets, and we wanted to see what is causing H alpha to vary. For one of the stars, it was actually spots. So on the top, we have a light curve or flux over phase, phase folded light curve, or brightness over phase. And you see that it dims and then it goes up and then dims again. So the dimming part is when the spot comes into view because it's a darker, cooler area of the surface, and so it dims the light. At the bottom, we have what I call a spectroscopic light curve, just because we're looking at basically the area under the curve for the emission line. And we're plotting it against phase. More negative means bigger. And so you see that H alpha increases when you have a spot in the view. And this happened for one of the stars. So we have two other stars where it wasn't really spots, or we didn't observe it enough to see spots, but we saw flares in their light curve. So again, this is a light curve on top. I've created lines where the flare happens. And the flare was tagged by a convolutional neural network named Stella. So Stella gets trained on flares with tests, and then it basically pops off a Roth estimate where the yellow is like, yes, probably a flare. And it does pretty well. As you can see, the outliers are in yellow. And so this target was observed for 100 minutes. And when you put the spectroscopic light curve on the bottom of it, you see that there is a bump where the flare happens, but then there's like a similar bump later and there is no flare. For this other star, they're much smaller flares because they don't have the stereotypical rise and decay. And so there's 4 of them. And when you look at the Balmer lines, it's really hard to see, but they have an actual better flare profile. This last one is actually a complicated one. Complex flare because it has an extra bump. And so what are the difference between these two? Well, the difference between a white light flare, which is the TESS flare, and a non-white light flare, which is the Balmer flare, is basically the corona magnetic field strength. So the Balmer ones are weaker, whereas the TESS ones are stronger. And you actually also see these on the sun. Okay, now we're switching gears in the next 4 minutes. Yeah, so now that we know that there's some intrinsic variability, we want to talk about that in terms of exoplanets. And for starters, I want you to learn a new term called obliquity. So a stellar inclination is the angle between spin axis and the line of sight. Orbital axis, line of sight. obliquity is spin axis and orbital. So it has to do with like the planet star architecture. If you have an obliquity of 0, this means that your planet is orbiting the same direction as your star is spinning. If you have one of 90, I call it the rotisserie, where you have the planet orbiting 90-degree angle to the star. And then if you have 180, that's basically your orbit is in the opposite direction of the stellar spin. Another term I want you to keep in mind is hot Jupiter. That's just a Jupiter-sized planet that's much closer in, so it's hot. And on the population level, for obliquities, we actually see that if your hot Jupiter is around a cool star, and this is defined by less than an F5, then it's an aligned system. So its obliquity is small. But if it's a hot star, its obliquity actually ranges in obliquity angles. And so this actually has to do with something called the Kraft break. And that is where there's a breakdown between rotation periods and like magnetic bracking and stuff like that. And it happens around an F5. And it's different depending on whether you see binaries or single stars. Okay, so having that in mind, there is this paper from Mazar et al. That looked at this in terms of inclination and photometric amplitude. So looking on the left side, if we have two stars, one is at 90 degrees stellar inclination and the other one's at 30, and you look below, you see that the light curve, that the photometric amplitude for the one that is at 90 degrees is much bigger than the other one. Okay, so let's take the maximum one and then let's put a planet around it. So if you have a planet that's transiting, you think its orbital inclination should be around 90. So now you have a stellar inclination and orbital inclination both at 90. This is considered aligned. And so if you compare this to stars that are randomly oriented, your amplitude for your line system should be bigger. And so that's what Mazar et al. Did in 2025, where they found the same results, that your cooler hosts have a larger amplitude than randomly oriented stars, so they are aligned, and the hotter stars have the reverse. And so my work was to go down to M-dwarfs, but also revisit. And so we went from 2 billion stars in the test catalog. We did a bunch of cuts that has to do with removing stellar inference from other stars, removing binary, do a test cut of magnitude to make it less noisy, and then do the parameter cuts. Make sure it has a period, which has to be less than 10 days, like I said earlier, or 13.5. And then we ended up with much, much, much less stars. And so if we just look at the M-dwarf part, you see that earlier your hosts had a bigger amplitude, so they were aligned. We're seeing the opposite of that. And so I'm almost done, I promise. And let's take a step back why we're seeing the opposite of that. So I revisited the Mazar et al. One with newer data and basically broke it down based on rotation period. If you look at the slow rotating one, so they rotate more than 13.5 days, that's actually causing that relationship I talked about earlier. Whereas you can really see nothing basically in the active star region. And so that's basically what we think we're seeing, is that we're seeing selection effects. We're looking at the fastest rotating stars. These are very active, and so they have a lot more stuff on their light curves than a star that had nothing in it. And it's also harder to find planets around these stars because flares and like spots and stuff like that. And so
Any questions? But it looks like everything was clear and we learned quite a bit about variability of stars. Thank you so much.
I want to invite everyone to stretch now that everyone's consumed their sandwiches. Get up. I don't know. Well, I set up here anyway. Yeah. Thanks. Hopefully. Right. Thank you, everyone, for sticking around so long. I apologize; it's running so late. And not only is this a talk about dust, it also includes math or equations, which I usually try and avoid. So I'll try and make this entertaining, and we'll all get out of here soon. So I'm Christina. I'm one of the new J.C. Ryan Fellows here that started in September, and I just wanted to give people a sort of a sense of the work I do and I'm interested in, and so hopefully, if you have similar interests or questions, you know where to find me. And so today, a lot of my work really is sort of, motivated by this concept that, the ISM in particular, dust grains are really important regulators of baryonic ecosystems of galaxies. So my main motivation is how do galaxies evolve over time? And so dust grains are sort of notable in that they, catalyze the formation of molecular hydrogen. They're essential for providing shielding for star formation. And they also process a lot of this, ultraviolet or higher energy radiation from stars into sort of infrared radiation. And so when we actually look at, for example, a galaxy's emission over a bunch of wavelengths, sure, there's a lot of stellar emission and the optical and UV kind of near infrared like we know of. But once you get into the further infrared regimes and beyond, a lot of that emission is dominated by dust emission, and that drives our inference of the galaxies themselves and the star formation rates that we're inferring. And so it's really important to understand where this dust emission is coming from, what's producing it, and what sort of factors are going to change it. And so, on first principles, dust emission is driven by a couple of different factors. So when we say dust emission, what I'm talking about is the surface brightness we observe. And the first sort of major thing that ends up, shaping the emission that we see is sort of the temperature of the dust itself. This is often modeled as a black body or a broken black body model that's sort of set by the intrinsic temperature of the dust grains. But then it's also, the actual amount of dust that we have. This is often quantified as the sigma d, or the dust mass surface density, which is just, at least for nearby galaxies, we quantify it as the amount of dust, kilograms, solar masses, something like that per unit area. And then the last factor that sort of is a lot of times marginalized over or sort of assumed to be constant is this concept of dust mass opacity, which can kind of be characterized as how much dust or how much emission do we expect an actual single, a couple of dust grains to produce per unit mass independent of temperature. And it has these kind of strange units to sort of cancel out the dust mass surface density. And so when we are actually doing this sort of dust fitting through emission is, hopefully we get a couple measurements of the flux in a couple of different wavelength regimes. And this is then our observed surface brightness. We can then infer some sort of temperature based on the shape of these measurements. And then once we have a, well-fitting temperature or estimate on the temperature, you can then scale this, with the amount of dust, this sort of surface density unit that we're really intrinsically what we're interested in, right? This is sort of going to tell us a lot about, what is the relationship between the dust and the gas, how much star-forming material is actually in these galaxies and driving our star formation estimates. The issue is oftentimes, though, is that we sort of, like I said earlier, marginalize over this dust mass opacity and assume that it's constant within a galaxy. We try and make good estimates, but a lot of times, it's not the driving quantity that we're interested in, and so to a first order approximation, it sort of gets marginalized over. And so, one way to think of it is that regardless of gas density, we sort of assume this dust mass opacity factor is constant. However, theory tells us that this should not happen. In fact, according to a lot of cool simulations back in the past and even more recent findings, we believe that dust mass opacity should be increasing as a function of gas density. And so it's very then puzzling when we actually try and go out and measure this, and the only observational evidence we have shows an inverse trend. This is work led by my collaborator Chris Clark down at Space Telescope, and he just told me before this talk, even he doesn't believe these results. And a lot of this is sort of driven by the fact that these inferences were done on, relatively nearby galaxies. They start with an M, so we know they were part of a, Messier catalog. But they're far enough away that they were performed on kiloparsec scales, which, if you're trying to characterize the temperature of a singular dust cloud at a kiloparsec scale, that's really hard to do. There's a lot of different radiation going on if you blend it to a kiloparsec. And so one of the motivating questions was, do we see similar trends at parsec scales? And so to actually do this, we end up trying to use dust extinction as sort of a proxy to calibrate these factors. So the sort of fundamental assumption we have is that if our kappa value, this opacity value, is correct, then the amount of dust mass surface density we should infer from extinction and emission should be similar. And so actually most of my work revolves around taking multiband photometry and processing it, creating dust maps and dust extinction maps in nearby galaxies. But we can then take these two, convolve them to the same resolution, and then see how do these actually agree. And so on the x-axis bottom here, it's just the dust mass that we infer from the dust emission versus the dust mass we infer from the dust extinction. And so again, if we, if the opacity is correct, and it is in fact constant, which it's not, we would expect everything to follow along that dashed darker line. And we can see that it is in fact not. It is offset, and it varies as a function. And so what's really cool is that we can then take, how much dust is expected from the emission versus the extinction, plot that as a ratio as a function of the gas density. And there an even more interesting trend emerges. So this is telling us that at high gas densities, essentially the emission is over-predicting how much dust we think there should be relative to the extinction. Assuming that our extinction measurements are correct, which is like another whole talk. And especially in the low gas densities, we're probably under-predicting the amount of dust there should be in the fields based off of the emission-based measurements. And so again, this trend indicates that our constant dust opacity assumption is definitely not correct and definitely not applicable in a nearby galaxy like the LMC. And what's interesting is that this sort of trend, if you actually then correct it, is indicating that essentially at higher gas densities, these dust mass opacity should be corrected higher to compensate if we actually wanted to correct this. And so I will sum it off here, leave people to go back to their working days, but I wanted people to take away that dust grains are interesting, and essentially bear in mind the fact that dust grains become more emissive is in denser gas environments. And this are some of the first observational evidence we have of these findings. That sort of corroborate our predictions from theory. And so I think the next sort of fun steps will be to, go back and reconsider the emission-based fits we have already, and see if we can also expand this into other nearby galaxies with different metallicities. I sort of, for what didn't really mention, the LMC is at 50% metallicity. Do we find similar trends at more solar? It's a whole nother ballpark we could just start to explore. So hoping to post this letter. Shortest paper I've ever written. I'm very, very happy. It was a delightful experience writing that compared to like a 20-page paper. But yeah, I'll leave it here. Thank you.
Beautiful results, Christina. Quick question: in terms of the mass budget of dust, how does it split among sources in your model? Or your understanding?
Amongst, what do you mean by sources?
Sources could be winds from stars or supernovae or just formation, in situ formation.
That is a whole nother, ballpark.
But it's important for the interpretation, of course.
So we're doing it on convolved process maps. We're not really able to pinpoint the sources of the dust production of that's the sort of ballpark.
Well, yeah, if it's supernova, then you will find it where massive stars exist. If it's something else, you will find it. So in principle, you can separate those sources.
Yeah. So I guess the issue is that at this for these, the emission maps, and we end up actually to get to the resolution of the gas densities, we have to convolve to like tens of parsec scales, and when you get into that regime, I just fear to assign responsibility to any particular source, and really should be hopefully driven by the gas density.
I have a question that's sort of related to what Avi's asking, which is how are you accounting for the variation in temperature within the smooth cells that you're looking at?
The smooth cells we're looking at. Yeah, that's another good question. Temperature.
Because if you go back to your equation for the flux on the previous slide. So that TD is not a single number.
No.
That TD is a distribution, which changes importantly with things like what the distribution of stuff and where it came from is in the box.
Yeah. So the dust maps are all, at least for the dust emission is calculated at the convolved lowest resolution for red maps. It is still at tens of parsec scale, but it's better than the kiloparsec scales that were being done previously. And so there
Honestly,
is,
the kiloparsec scales would probably wash this out better.
yeah,
But no, there's a lot of papers by Rahul Shetty and Brendan Hensel.
Yeah.
About this, yeah.
Yeah, for sure.
It was a problem.
Morgan?
Something I've been confused about, so this question might not come out perfectly, is essentially the slope of kappa as a function of wavelength,
Yeah.
which I think relates to the like relative extinction. So how does that work in this context? Because different environments might have both a different normalization and different slopes, and can you probe that at all? Like, as I understand in the
yeah,
LMC, like RV is different.
yeah.
What do we, can you
Can I speak to this? Well, so what I can say is that the dust, so all of the emission work was done by my collaborator, and we used a kappa set at, that was measured at 160 microns. And so we can sort of, calibrate or recalibrate the 160 micron measurement. So that's really what I'm showing here is originally actually the value assumed for the opacity, for the original dust emission inference was set by this Roman Duval value. And then when we, try and recalibrate using, this trend line that we observed, we see the following distribution that ends up spanning, an order of magnitude, sort of like theory would probably have predicted. Extrapolating from that 160 micron into other wavelength regimes is something that would require refitting the emission data itself, but it's something, I'm not going to be the one to do that. I will be honest, that would be something Chris would have to undertake. But he's mentioned he's interested in it, but it would, sort of was beyond the scope of the initial finding. But it's definitely something on our docket, and I think from there you could start to do interesting inference or, as a function of different wavelengths.
Okay. Yeah, thank you.
Any other comments, questions?
I misunderstood.
Okay, sure.
Let's thank Christina again.